Okay, hi everyone. Let's start working on the homework. So this is homework 2 for chemical reaction engineering. And this homework you're introduced to new ways of solving problems. So just follow along. If you're having a hard time, just come to office hours. We'll work on it. We'll get there, okay? So problem number 1. Liquid A decomposes by first order kinetics and in a batch reactor. And in a batch reactor, 50% of A is converted in a 5-minute run. How much longer would it take to reach 75% conversion? So if you remember, this week we talked about interpretation of batch reactor data, and you basically have 6 cases. The approach to solving this problem is you need to identify the case, find the performance equation, plug in your numbers, do some algebra, rearrange the equation, find your answer. This is really the approach for almost all the problems, except one, I think, where you have to plot a few things. Okay, so let's start by doing problem number 1. Let me go to the whiteboard here. Hopefully this works. All right. Okay. So let's see. So we're doing basically homework number 2 in CHEN 422. And problem number 1, you're being told that A decomposes to some products. And because it's a decomposition, it's an irreversible reaction. And usually, unless you're told it's reversible, you can assume that it is not reversible, right? You're being told it's first order kinetics, and you're given 2 cases, or 2 scenarios. Let's avoid using the word case to avoid confusion. 2 scenarios. Scenario number 1, you have XA1 is equal to 0.5 when T1 is equal to 5 minutes. And scenario number 2, you have XA1 is equal to, XA2, this case is equal to 0.75, and you need to find T2. So if you recall, for case number 1, right, I have 2 governing equations or performance equations. The first one is minus ln Ca divided by Ca naught is equal to Kt. And this is the performance equation with respect to concentrations. I also have the performance equation with respect to conversion, which is minus ln 1 minus Xa is equal to Kt. And because I'm given information in terms of the conversion, I'm going to use this second equation right here. So let's plug in. So if you look at this, Xa and T, I'm given some information about them. I'm really missing this parameter K right here, right? Maybe right here, right? So I need to use the scenarios from condition 1, get K, and then use the XA2 to get T2. So let's do this. So I'm gonna plug XA1 and T1. So basically minus ln 1 minus 0.5 is equal to K into 5 minutes. And from here, it's clear that K is minus ln 0.5 over 5 minutes. You can get numbers, but keep track of the units, right? So now I have K, and now I'm gonna just plug XA2 and get T2. So in this case, minus ln 1 minus XA2 is 0.75, right, is equal to K T2. And in this case, I know that K is minus ln 0.5 divided by 5 minutes T2. So you can solve for T2 to get minus ln 0.25 divided by minus ln of 0.5 multiplied by 5 minutes. And this fraction is basically equal to 2. So you're going to get 10 minutes for T2, right? And the question is asking you how much longer would it take to reach 75% conversion. So if T1 is 5 minutes and T2 is 10 minutes, so it takes 5 minutes, right, to get from point A to point B. So this is problem number 1. This is the general approach to solving these types of problems. Get used to basically using an equation twice where you use one set of conditions to find your K or to find your CA note. Then once you know these parameters, you're going to use the same equation again with your known constants to find a new time, a new conversion, whatever you're being asked to do. Okay, so let me save this guy here. It's saved. Let me make sure it's sharing. Good. Okay, so now let me clear. And let's go back to the homework and have a look at problem number 2. So problem number 2, you're being told, repeat the previous problem, but for second order kinetics. Okay, that's fine. So let's go to the whiteboard. And now we're doing problem number 2. And in this case, you're being told, repeat number 1, but you have second order kinetics. So if you recall, second order kinetics means we're going to use case number 2, right? So second order kinetics is case number 2, which from your slides is for an irreversible second order reaction, right? So case number 2, irreversible second order. And if you recall, for case number 2, we have 2 equations. The first equation is for bimolecular second order, which is basically A plus B going to products. And the second case is for unimolecular, right? And in this case, I just have 2A going to products. And in this problem, because you're being told in problem number 1, basically liquid A decomposes, so we'll be looking at the unimolecular case. Sorry. And in the unimolecular case, so we'll be looking at unimolecular, and the performance equations in this case are 1 over Ca minus 1 over Ca naught is equal to 1 over Ca naught Xa 1 minus Xa is equal to Kt. So because we're given information in terms of Xa, I'm going to use basically this part of the equation. And again, if you recall, you're given 2 pieces of information. First one is Xa1 is equal to 0.5 and T1 is 5 minutes. And the second set of the second scenario is Xa2 is 0.75 and you need to find T2. Okay, so let's plug them in here. So I have 1 over Ca naught, 0.5, 1 minus 0.5 is equal to K, 5 minutes. So as you can see, it's clear from here that I also don't have Ca naught. And I also don't have K. So I have 2 unknowns. However, this is also, if you do a loss transport problems, it's always good practice to lump your unknowns into one big constant, basically. So if I lump them together, 0.5 over 1 minus 0.5 is basically 1. So I'm going to get 1 over 5 minutes is equal to K Ca naught. So basically, I'm just lumping my unknowns. And this makes it easier for me to reach my solution, because I just lump them. It's just a manipulation because you don't have really enough information to get 2 separate constants. Okay, so once I have K Ca naught, I'm going to plug it again in the second time into the equation. So I have 1 over Ca naught for the second scenario. So let's write this is 1 and this is 2. Xa2 is 0.75 and then 1 minus 0.75 is equal to K 5 minutes. And this is what? This is 0.75 or 0.25. So this is 3. So basically I can write 3. Sorry, this is not 5 minutes, right? This is T2. We're trying to find T2 in this case, right? K multiplied by T2. So in this case, I have 3 minutes divided by K CA naught is equal to T2, and KCA naught is 1 over 5. So basically this means that T2 is equal to 3 multiplied by 5 and 15 minutes. So T2 in this case is 15 minutes. So the time it takes from XA1 0.5 T1 5 minutes to XA2 0.75 and T2 equals 15 minutes in this case. It takes 10 minutes to get from this point to this point, and this is your final answer for this problem. Okay, and again, just so the unique thing about number 2 is this manipulation where you lump your constants, right? And this is a manipulation you're gonna have to do a bunch of times. Let me save this, and let me pause the recording here. We're actually